Hello there, welcome to my channel. So in this video I will be showing you one of the shortest methods of solving second order differential equations. This is a very useful tool in mathematics, physics and engineering. So as we all know, our second order differential equations, we always have two parts, the complementary function and the particular function. But instead of solving this the normal way that you look for the complementary functions and you also look for the particular functions, taking note of the general form of the the complementary function. And we will apply what we call the operator D method. Now, the operator D method here, there are just few things to take note. D means d over dx. D square means d square over dx square. 1 over d means you are integrating once. 1 over d means you are integrating twice. Okay, let's quickly solve this problem here. So, given this problem, we start by looking for our complementary function. Let's replace this with a letter of the alphabet, say A. So this will be a squared minus 6a plus 9 equals to 0. This is our complementary function. We are solving our complementary function where a equals to what? A equals to dy over dx. We just substitute it as the normal way that we solve our second order differential equation. If you don't know how to solve second order differential equation, you just look through other videos that actually give an introduction and the ways to solve it. This video is just to bring out the shortest way to solve it. Okay? So quickly, if we factorize this, we have our complementary function solution, and we have this to be a minus 3 and a minus 3. If you should factorize this quadratic equation we have here, this is a quadratic equation here. A squared minus 6a plus 9 is equals to 0 is a quadratic equation, and we have this as the root. So this gives us that, this implies that our a equals to what? 3 twice. We have that. Now we know that our general solution, when we have equal roots for the complementary function, the general solution will always take the form of what? Our y will be what? Exponential 3x into a plus bx. This is always our general solution. This is always our general solution when the roots of the complementary functions are equal, have real numbers that are equal. So, having gotten the complementary function solution part here, okay, what our aim now is to introduce our operator and solve completely to get the complete solution. Alright, so record this because that's what we are going to use now. So applying this into this equation, applying what you have here into the first equation here. Let's call this equation 1. So applying that into equation 1, we will have this. This will be d square y from equation 1 we will have, applying the operator, this will give us what? This will give us d square y minus 6d. Remember, d is d over dx. Y, okay? Plus 9y equals to what? Cos 2x. Alright? Okay? Let me flip the board over. Okay, the color is not really showing with the marker, so just erase what we did and so that we can use the white side. So as we solve our equation, to the point, and we got our complementary function to have this general solution here. All right. So now to get our particular integral function solution, we apply the d operator to this equation, and this gave us this. Using that, all right, this will give us, if we should factorize this side now, we factorize this, we should factorize that, we will have d square minus 6d plus 9y. Y is common there. That will give us cos 2x, as was there in the question originally. Okay? So we should make y subject of formula. You have that y equals to cos 2x divided by the square minus 6d plus 9. Okay? So this is where you actually need to understand what the operator here does. Of course, this will be written as this. This means that this operator here will operate on cos 2x. Alright? Okay. Now, there's a standard convention here. Anytime this operator D operates on, sin AX or cos AX, and the operator is operating on it in this manner, what we do is we take whatever function it is operating on and we make the substitution of this. What this tells you is, if we have a trigonometric function sine ax or cos ax, and the operator is operating on that function in this manner, like integration, as we said earlier, that when 1 is 1 over d is integration. What it tells you is wherever you see a, you replace it with minus a all squared. Alright? For this our problem, what will be a? A is 2. Okay? A is 2. So what do? We include our operator there, and this will be y equals to 1 all over. Wherever you see d, you replace it with minus a all squared. So this will be minus 2 all squared. Wherever you see what? D squared. Sorry, don't get it mixed up. Wherever you see d squared, not d. So this will be minus 6d plus 9 cos 2x. Okay? So doing that, that will give us, this will be minus 4 minus 2b equals 1 over minus 4 minus 6b plus 9 cos 2x. Of course, this will give 1 all over minus 4 plus 9 will give you 5. 5 minus 6d, and it's operating on cos 2x. So our aim is to get this to get it to operate directly on this. If we go this way, we might not really get a good solution. So if we take the conjugate of this, you will have, we take the conjugate of the denominator here and multiply by the numerator and denominator. So we will do this 5 plus 6d all over 5 minus 6d. 5 plus 6d. When you multiply 5 plus 6d to the numerator and denominator, so that we can get something that we can easily use and operate on cos 2x. It's just the same thing. We are just trying to make a conjugate of the fraction. So these are difference of 2 squared. If you don't know what difference of 2 squared is, when expanding and factorizing, you check it out. So this will give us what? This will give us 5 plus 6d all over 25. Okay, let's just make it different so that we understand what we're doing. 5 squared minus 6d squared cos 2x. This will be 5 plus 6d all over 25 minus 36d squared cos 2x. Okay? So we can see that okay, let me write this out here again. We've gotten 5 plus, let's write that part again. This implies that we have gotten 5 plus 6d divided by 25 minus 36d squared to operate on cos our cos 2x. We've noticed that we have gotten this parameter again here. And remember, any place you see d squared, you replace it by what? Replace it by minus 2 squared. Since our a was what? Our a was equals to 2. So this will give us what here? We have 5 plus 6d all over 25 minus 36 into minus 2 squared. Cos 2x. Alright, let's erase some parts. Okay, if you multiply this out, you will have 5 plus 6d all over 169 cos 2x. You can see now that we can easily apply this to this now. So this means that we can expand this, can easily expand this and interact directly. This will mean that we have 5 cos 2x bracket close over 169. We also have plus 6d cos 2x over 169. Recall that d is the same thing as what? D is the same thing as d over dx. Means you are differentiating whatever is here once. So this will give you what? If d is the same thing as d over dx, this will give you, let's erase that. This will give you 5 cos 2x. Okay? Divided by 169 plus, alright, the differential of cos 2x. Differential of cos 2x will be what? Minus 2 sine 2x. So this will be plus into minus 2 sine 2x. So you see the operator is gone. So our particular integral function is what? A particular function will now be 5 cos 2x divided by 169 minus, there was 6 here, we have 6 here, that will be minus 12 sine 2x divided by 169. And recall, our solution is what? The complementary function plus the particular function solution. Okay? Alright. This will give us a complete solution of, general solution of this, because our solution is what? Y equals a complementary function plus particular function solution. So this gives you y equals to exponential 3x a plus bx that we got here, plus the particular integral solution here. Now, what you should note is that d is what? D over dx. The square is what? The square all over dx square. The square is the square all over dx square. Then integral of d over dx is what? 1 over d. And for sine ax or cos ax, 1 over the function d in terms of d square. you replace this square with this minus a square, where a is the coefficient of x in the trigonometric function cos or sine. Okay, all right. I'll take one more example so that we really clear ourselves on what this is about. Okay. Okay, for the second example here, we have the square y over the x squared minus 4dy over the x plus 4y equals to x cubed exponential 2x. Alright, we know our normal solution is always a complementary function plus the particular function. Okay? So, quickly, let's factorize to get our complementary function. Let's make this. To get our complementary function, we quickly factorize this again as we did the other time. This will give us a squared minus 4a plus 4, where our a is substituted with dy over dx. So solving this quadratic equation, we will factorize it to have a minus 2 and a minus 2. That gives us equal roots. So that means a equals to 2 twice. Okay? And we know when that happens, our general solution is what? Our general solution for the complementary function will now be exponential a, which is 2 here, x, bracket open, a plus dx. Okay? Now, we have to look for our particular integral. To get our particular integral solution, we follow the same steps as before. Follow the same steps as before. Okay. The square y over the x square will be replaced with d square minus 4 d square y minus 4 dy, this for this, plus 4y. That gives us x cubed exponential 2x. Alright? You can factorize this. You can factorize the whole of this. You can factor out y to have d square minus 4d plus 4y. That will give you what? X cubed exponential 2x. Right? Okay? So you can now say that y should be, making y here the subject, exponential cube exponential 2x all over d square minus 4d plus 4. Okay, having done that, we are now looking for ways to operate this on that. So let's see what we will get. We should make if we should make this to operate on this, this will give us something of this sort. Now notice we want to operate on a polynomial function and an exponential function. Okay? Now to operate on a polynomial function and an exponential function, in such a situation that we operate on that, we replace d. D will be replaced by d plus 2 when operating on an exponential function. Now the strategy is here is if you are operating on an exponential function of a raised to the power x, okay, what you replace is you replace the operator d with d plus a, okay, and in this case we are operating on a polynomial function and an exponential function. What we do is we first of all operate on the exponential function, then we now go on to operate on the polynomial function. Alright, so let's do that. Let's do that, and this will give us alright, this will give you what? If you expand it, you have d squared plus 4d plus 4 minus 4d minus 8 plus 4, and this is operating on x cubed exponential 2x. This will go with this, and these two, and this plus this will take this out. So you'll be left with 1 over d squared x cubed exponential 2x, because we've already operated on this, so this will be what? Exponential 2x one over d squared x cubed. So what do? We integrate it how many times? This is the operator now. Recall 1 over d squared is what? You integrate it twice. So this will give you what? The first integration will give you exponential 2x. Alright? and the first integration will lead it down to 1 over d, and this will be x4 all over 4. Again, you will still integrate it again to get this out. The exponential 2x, this will now be x5 all over 20. If you all know how to integrate. So our particular integral is this. So our general solution will now be our complementary function plus our particular integral. This will be exponential 2x a plus bx plus exponential 2x x raised to the power 5 all over divided by 20. Okay? Alright. Thank you guys for watching. Recall, what you should take note here is when you are operating on a polynomial and an exponential function, you make the operator to operate based on the exponential function. And what you do is you replace the operator d by d plus whatever is the coefficient of x here. In this case it's 2, so you replace it by 2. Alright? And that's it for the tutorial. You can see it's a very quick method to solve and second order differential equations like this. Now imagine if you were trying to solve this using the normal and the conventional way that you solve for the complementary function, of course, and you now start to be looking for the particular integral by making bringing in yp1, yp2. It will be a very long and tedious process, but you can see we just did this, and we arrived at the solution. It actually took us how many steps to complete that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright, compared to the other method. Thank you guys for sticking around to the end of the video. I hope you liked the video. See you next time.